what does it mean to be similar? We already know that congruence, right, means identical. Think about that. Congruent means identical. They're same shape, same size, all angles, all corresponding sides are exactly the same measure. Okay? Similar figures, triangles, quadrilaterals, whatever, okay, they don't have to have the same shape and size. They do have to have the same shape, but not necessarily the same size. Okay? So, similarity transformations, now, we're going to talk about similarity transformations, is a transformation in which we maintain similar objects, similar triangles or whatever, similar quadrilaterals, but they may not be congruent. In other words, the size can change, but the shape will remain the same. Okay? So like we already know isometric transformations. We learned those earlier in the year. Isometric transformations or rigid motions. All right, I'm going to put that next to here. See, isometric transformations is also rigid I'm going to put it right here. Rigid motions. Okay? Isometric transformations are rigid motions. Those are reflections, rotations, and translations. We should already know that. All right? Our rigid motions, our isometric transformations, our reflections, rotations, and translations. When you do a reflection, same size and shape. If you have a triangle, here's a picture right here. Triangle ABC reflects over line L, becomes A prime, B prime, C prime. Same size, same shape, right? So a reflection keeps the same size and same shape. A rotation does too. You just turn it. It doesn't get bigger. It doesn't get smaller. Translation, you just slide it, right? Slide the figure. No shape change, no size change. But a dilation is a size change. However, it keeps similarity. So a similarity transformation is all of these things. They are all similarity transformations. A dilation is, and reflection, rotation, translation. Because if you're congruent, you're also similar, right? You wouldn't, if I said two things are identical, right? I'm not going to say that they're not similar. They got to be at least similar to be identical, right? We're just going further and saying they're congruent, they're identical. Someone might say, well, they're similar. Well, yeah, they're similar. I say, no, they're exactly the same, all right? Now, a dilation changes the size and shape of, say, a triangle or a quadrilateral or whatever we're dealing with. All right? They're all transformations. So this diagram here, this little Venn diagram here, shows that all of these things are transformations, right? Dilations are similarity transformations, and reflections, rotations, and translations are isometric transformations. Okay, so that is kind of how it works. Definition of similarity is when two figures are similar if and only if one can be obtained from the other by a single or sequence of similarity transformations. So basically, that's the definition. If you can do any of these things, if you can do a dilation, a translation, a rotation, or reflection, if you can do any of those transformations and you get the other figure, you have two triangles, right? If you could do any combination of those things, get from here to here, you have what's called similar figures. That's what we're going after here, okay? So, and here's just some notation for you. Remember, this means congruent. Why does it mean congruent? It means similar in shape, equal in measure. Got it? Similar in shape, equal in measure. Similar in shape, equal in measure. This means similar in shape. So the symbol for similar is just going to be a squiggle. All right? Congruent was squiggle equals. Because why? Because not only was it similar, it was also equal in measure. This is just going to mean similar. Just similar. Okay? Means same shape, different size. So here's a similarity statement here. Triangle ABC is similar to, okay, is similar to, can't write today. Wow. Is similar to. That's what that symbol right there means, is similar to. Triangle ABC is similar to DEF. See the picture right here? ABC is a small triangle. DEF is a larger version of ABC. It's the same exact shape, the same angles, same angles. Angle A equals angle D, angle B equals angle E, angle C equals angle F, but the sides got bigger. The sides got bigger, all in a proportion, and that's what similarity is all about, guys. Very important to understand that. Angles are congruent. When we talk about similar figures, angles are congruent. Corresponding angles, just like in congruent triangles. But the sides are not congruent. Obviously, look at much larger sides. One of them's longer, right? AB is much longer than DE. No, it's not. I said that wrong. DE is much longer than AB. DF is much longer than AC. Okay, so you can see that. But they are proportional. They increase by the same exact amount. So DE relates to AB. Corresponding, just think corresponding sides, right? DE is a ratio to AB. DE is to AB as EF is to BC as DF is to AC. Okay? So they're just relate, the sides are in proportion. So examples of that. So if I have triangle ABC, I'm going to draw a triangle. ABC. Okay? A, B, C. Now I'm going to draw a smaller triangle, but it's going to be the same shape. Kind of. And then I call it MRG. MRG. Now see how I labeled it? I went top, bottom left, bottom right. Top, bottom left, bottom right. You got to make sure they line up. A corresponds to M, B corresponds to R, C corresponds to G. We should know that already. We've done that earlier in the year, right? Same thing with similarity as it was with congruence. Okay, now, the sides are smaller, but the angles are still congruent. So angle M will be congruent to angle A. So that's going to be angle A. The sides are proportional, so RG is corresponding to BC. See that? Red, red. GM, green, is going to correspond to what? AC, right? AC. Pretty simple? Okay. And then this one here, MR, we'll make that black. MR corresponds to MG. Okay, so MR and MG, see how it goes like that? MR, MG. How would we relate these two? Okay, well, MG is going to match AC. See how they're both in the bottom of the proportion? MG is going to match AC. So I'm going to make that black. I'm actually going to change the color back to blue here. Change that back to blue. I'm going to make that blue. So we can see the corresponding pieces, right? So if MG matches AC, then MR must match AB. So I'm going to put AB there. Okay? And that's it. So the answer is AB. You get the idea, guys? All right. Angle T matches without even a diagram. T would match Q. I got to put angle Q. Angle Q. Because it's the middle letter. Simple. ST is to TV as WQ is to QY. See how it's got to be the exact same? So this will be QY. QY. All right. And then let's start over again. YW. YW is to QY as blank is to TV. Well, YW has to match VS. 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 Just use the letters the way they're presented to you in the similarity statement. You don't even have to draw a picture. But if it helps to draw the picture, do it like we did in example 1. Now, establishing similarity through similarity transformations. This is what we talked about on the front page. Dilation, translation, reflection, rotation. You could do 1 of them, 2 of them, 3 of them, 4 of them, 5. We're not going to do that many. You could do a dilation, then a rotation, then a reflection, whatever. If that happens, you have what's called similar figures because you did similarity transformations. We're just going to do 1 or 2 or 3. We're not going to go crazy here. This one's already done for you. So here's the original. Okay. Now not the original. This is what is going to happen. This is like the final answer. See this right here? OBCD, this one right here. This quadrilateral became this quadrilateral. So quite obviously there's a dilation. It blew up. How much bigger did it get? Well, we're not sure. Okay? But what they showed us here is it went 2 units and then went bigger 2 units. So it went up to 2, and then this one went 3 units and then another 3 units. So that seemed to double. And then it went over 2 and up 3, then over 2 and up 3 more. So it goes over 2, up 3, over 2, up 3. So that seemed to double. So that's double, and that's double, and that's double. It looks like everything doubled, and then it rotated 180. And then it rotated 180. Okay? So you could see how it dilated and then rotated 180. And that's what they kind of showed us here what it was. It's a dilation of 2 and then a rotation of 180. That's how we got from the purple or the violet to the purple, or purple to the pink, whatever that is. From OBCD to OHLK. All right, there was a dilation of 2, and then there was a rotation of 180. That just shows you how they're similar. These are similar quadrilaterals. These are similar quads. I'll put similar quads. And the reason they're similar quads is because there were similarity transformations, a dilation and a rotation, that got me from one to the other. We blew up the one and then we rotated it around. Determine the sequence of similarity transformations that map one figure onto the other. So and I've already done this just to kind of go a little quicker. Sometimes it's tough, but you can tell there's a dilation in both of these, right? Okay, there's a dilation, then what happens? Well, what happened here? Now they're saying go from OBA to ORG. So we're starting with the big boy, going to the little guy. All right, so starting with the big boy, it's a dilation of something, a fraction. It got smaller. So it's a dilation. Now what happened? Let's try to figure out what happened here. So O didn't move. O doesn't move, so we don't have to worry about O. B, looks like B went to R, and looks like A went to G. So what happened? Well, it got smaller first. Okay, so what happened? How do I go from O to B? It looks like I have to go 1, 2, 3, 4, 1, 2, 3, 4, 5, 6. So the slope, or 6, 4, right? 6, 4. Up 6 over 4. So my slope is 6 over 4 for this guy. I should write that here. Slope is 6 over 4. And then for this guy here, my slope is up 2 over 3, right? Up 2 over 3. Okay? So, it looks like B went to G then. Up 1, 2, 3 over 2. Up 3 over 2. So B went to G, and it's up 3. My slope is 3 over 2. So what happened? Instead of going up 6 over 4, it went up 3 over 2. See how these chopped in half? Okay, it chopped in half. That means it was a dilation of a half. That's how you can tell. So what I'm going to do here is I'm just going to do my dilation of a half. Right here. 1, 2, 3, 4. Right? And then up 6. 1, 2, 1, 2, 3. That chopped it right in half. See how this is the midpoint of OB? So this is a dilation of the origin of a half. of triangle OBA. Okay, that was the first thing that happened. That equals triangle OB prime A prime. Okay, let's do A prime. 1, 2, 3, 4, 5, 6. 1, 2, 3, 4. 1. Cut that in half. 1, 2, 3. 1, 2. Boom, there it is. There's my A prime. There's my B prime. See what happened there? So I just cut it in half, okay? And I'm kind of drawing it right here. And you could see my triangle. I did it in red so you could see it good. There is my dilated triangle. Dilated smaller. Dilated smaller because it got dilated by a half. It got half as big as what it already was. Now, see the red? And then how it would flip over to the purple, if that's purple or blue, okay? If it would flip over the y-axis. So that's what it's followed by. Reflection, y-axis of triangle OB prime A prime equals triangle OGR. Okay, equals triangle OGR, and that is it. So we have a dilation of a half followed by reflection over the y-axis. Pretty simple. This one here looks like it dilated. Now we're going from ETHP to ODBA, so we're going from the little guy to the big guy. We're starting with the little guy. Starting with the little guy. Looks like we dilated. What do we dilate by? Well, let's see. E to P is 2 units, and then it's 1, 2, 3, 4, 5, 6 units. So it went 2 units to 6 units. That's a dilation of 3. All right. Let's dilate. Let's just dilate about this point here. It's easier because it's kind of going in that direction. So we'll start with E. It's going to be easier to do that. So we'll dilate from point E, and we'll dilate 3 units. We're dilating ETHP, and it's going to equal E T prime H prime P prime. We're going to find the primes. Okay, so let's do the dilation first. So I got a triple. It's 2. I got to go to 6. Boom, 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 boom. So here's my P prime. H is over 1, 2, 3, up 2. So I'm going to go over 3, up 2, over 3 again, up 2. Okay, so there's my H prime. My T is over 1, up 3, over 1, up, boom, 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 over 1, boom, boom, boom. There's my T prime. Again, we just tripled the slope. Triple the slope. Do the slope 3 times. Okay? And we have our, we've done this before. We've already done this. So we got our dilation. I'm going to just extend it with dotted lines so you can see what I'm talking about here. See that? See how it blew up, and now it's the same as the yellow one, same size, same shape. It's now congruent to the yellow one. So now I just need to slide it over. How do I slide? I slide with a translation. So we need a vector. What are we translating by? Well, we just got to move. Let's see. E has to go to O, and it's at -8. It's got to go to 0. This is at -2, and it's got to go to 6. We got to go 8 units to the right. That's going to be 8, 0. And what did we translate? We translated E, T, prime, H prime, P prime, and that's going to equal our final answer, ODBA. Quad. You should put quad in front of each of those. But see, so we did the dilation, we blew it up, made it congruent to that one, and then we slide it over. So we did a dilation about point E of 3, and then we did a translation 8 units to the right. And I will see you in class tomorrow for some more practice on this.